So yesterday, we left off because we were discussing the spirometry and how that's a test for the pulmonary function. And the pulmonary function is tested based on those volumes. And then those volumes can be used in some mathematical equations to determine capacities. And between the volumes and the capacities, that can be helpful for like monitoring the breathing. Say, for example, I think we talked about after surgery, okay? And then it can be monitored for any other type of lung disorders. It could be monitoring to see if there's maybe degenerative changes that are taking place. So we left off at the point where we talked about restrictive and obstructive. Emphysema is considered COPD, Jill.
Okay.
Yes.
Thank you for checking.
And I guess I was thinking that it was one that was to itself, but they have classed it with the COPD disorders. So, if you remember, we've got the restrictive versus obstructive. The restrictive means we're reducing the ability or the ease with the system does its job. In the obstructive, we're blocking or narrowing the airways. So now we're going to move into part 3. And part 3 begins to talk about the gas exchange and the transport. And don't forget that we are dependent upon the blood system, okay? The circulatory system, these blood vessels. Did I get to this one right here? I know we talked about Dalton's, right?
Yes.
Okay. And we looked at the partial pressures and the partial pressures of like the CO2 and the O2. And so now, as we begin to look at the gas exchange, the alveolar gas exchange, the alveoli are where? Not a trick question. In the lung tissue. Oh man, I left mine over here yesterday. Okay. All right, so now, remember, there are 2 places that we have to have the gases exchanged. We've got to have the gas exchanged in the lungs, so that means at the alveoli, and then we have to have the gas exchange at the tissues. So if we're at the alveolar gas exchange, we're down here at all the grapes, okay? And I should have reversed the colors, but anyway, y'all know by now. All right, and then we've got our capillaries, okay, that are around this structure very heavily. See how they're trying to represent? Okay, they're trying to represent all these capillary beds around one of the grapes. Okay, see how they're trying to represent it? Okay, around one of the grapes. Okay. How they're trying to represent the capillaries. So, the one thing we've got is a huge blood supply. So now, if I flip it around, they're trying to give me this view showing a very strong blood supply into an alveolus. Okay, this whole, you know, as we look into this, and we've got these little things making up the sacs, they're trying to show me how much of a blood supply I've got at the level where exchange is going to occur. So, where the exchange is going to occur, do you guys remember how I mentioned that we have a membrane, and that membrane is made up of the cells at the end of an alveolus, and then the beginning cells, and then the stuff in between, and we've got this being our respiratory membrane, okay? So see how they're trying to show the cells of layers that would be present? Not very many, okay? And in between that is the fluid. Okay, do you guys remember the plural fluid? Okay? Now, the gases, oxygen, nitrogen, all right? We've got to be exchanging at the level. Now, we have a law. I wish they quit moving my pointer. The air in that alveoli is going to be in contact with a film of water. Oxygen needs to dissolve in the water to cross that respiratory membrane and pass into the blood. And then the opposite direction, carbon dioxide needs to dissolve so that it can go across the plasma, go across the respiratory membrane into the alveoli to be breathed out. So these gases need to be able to dissolve in this water film. And the back and forth movement is the gas exchange in the alveoli. Gases want to move down their concentration gradient, and that was based on Dalton's law about the partial pressures, because the partial pressures, the higher it is on one side, it's going to diffuse to the other. Now, Henry tells us at the constant temperature, what's the supposed temperature of the body? 98.6 or 37 degrees Celsius, all right? So, at the constant temperature, the amount of a given gas dissolved in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with the liquid.
How's that different than the other law?
What?
Because it's becomes liquid.
It has to dissolve. The other law is just strictly the pressure. What is the pressure? Now, what is the dissolvability? Does that make sense? How dissolvable is the gases in this film of water for movement? Now, the overall goal at this alveolar level, unload the CO2, load O2. That's the overall goal, okay? But all of these factors, all of these gas laws, believe it or not, are playing a factor. okay? The pressure gradient will affect the movement. If we don't have a high pressure gradient, there's going to be little movement. Is that correct? Now, when we look at Henry's law, the unloading, the loading, everything for the gas laws, for the most part I should say, at the gas laws, we're dealing with it being at atmospheric level, sea level, okay? 1 atmosphere. But we know that as we move from sea level up, the composition of air changes, okay? So, these pressure gradients that can change, okay, as we go from somewhere higher than sea level, and we're almost at sea level here, okay, in the Richmond area. But we do have areas where altitudes are higher. And they talk about the air is thinner. Have you ever heard that? Okay. Yeah. All right. The pressures are different for the makeup of the air. Have you guys ever heard of a hyperbaric chamber? All right. What does it do?
Equalize pressure inside your lungs. Equalize.
I thought it forced oxygen into you.
Not so much as equalize force, okay? You get into the chamber and you're exposed to different atmospheres of pressure. The overall goal is to try to move oxygen from the lungs into the tissues of the body. Does that make sense? Okay?
So at higher elevation, the pressure's lower or higher?
Pressures are different. When we begin to look at the, like if we go to Mile High City, all right, if we go to Denver, you hear them talk about, well, the air is less dense, okay? What they're telling us is oxygen levels are not as great, okay? And the body compensates for that by increasing the red blood cell production so that it can pick up more oxygen so that it can carry it to the tissues of the body. So the pressure of oxygen at that level is not as great as it is here at sea level. Okay? In the hyperbaric chamber, they change the atmospheric levels, okay? And what that's going to do, it's going to force your body to hopefully respond with the red blood cell production, the oxygen pickup, and that sort of thing, all right? It's used for certain disorders.
I think about when people get the bends coming up from
Yeah,
scuba
they can
diving
do
too
that for
fast.
scuba diving. Like if they come up too quickly and they develop an air bubble in their blood system, okay, they can be put into the hyperbaric chamber to try to dissolve the air bubble. I'm not getting into that. So, yeah. Where
Isn't
you
that what
might,
Michael Jackson slept in or something, a hyperbaric chamber? Well, I thought he did. I thought he had one in his home to oxygenate or something.
yeah, it increases the oxygen level in your blood. I don't know.
I know that's weird. Sorry. I
No,
swear I read that 100 years ago. That he had a hyperbaric chamber in his home.